and Peter Allen and Nick, and yeah, they just asked if I could come along and give a talk and join Interglide. And there are still a few people around who might know me or recognize me from way back. No, everybody's shaking their heads. And it really took about 27 years for me to fly another Interglide. The last Interglide I attended was 1998 in Upton 7, and since then we didn't get the chance to come to England. I'm very happy that I'm here again and that I was invited. And just as I would say, kind of gap filler, we will have a little question and answer session. Of course, we try to do it a little bit more on a seminar or workshop base, but to do it whilst a competition is running, there's very little time. So I think we will have the dinner later, and thereby we didn't set up a computer with slideshow and so on. I would have something with me which I prepared. If there are questions later on, maybe for tonight or for tomorrow night, I could definitely bring the laptop and we could take a look upon that if there are more specific questions. As most of you know me from F5J, that is what I was doing a very, very long time in my life. I started with it in the 90s, and then I flew several world championships, several European championships, won the Contest Euro Tour several times, and then my life changed after the new 2.4 gigahertz technology was arising, and we got the possibility to have a GPS course set up to fly around that course. So this is what I mainly do right now. So there's not that much time left in my life to do thermal soaring the old-fashioned way, where you do duration mainly, like in F3J or nowadays in F5J. Nevertheless, it's a very testing and very tough competition, and I liked it a lot today, especially with the wind. That makes it more interesting. And as I understand, I could do a lot of talk about this new GPS class, but I guess you might be more interested in more specific things. Like when I was out there, a lot of people were coming across and they were asking, Philip, how do you set up this? What is your recommendation for that? How do you design aircrafts? What is the main important part when you design for this and that? How do you set up your flaps? And you come from one topic to the other, and the talk is getting longer and longer, and I see that there is mainly the most hunger in searching for some satisfaction to really get the right answers. And I would be open to discuss about that today. I would like to start with a small introduction about what's really interesting when you design an aircraft, because a lot of people understand what an airfoil is, a lot of people understand what an aspect ratio is, a lot of people understand what wing loading is, and so on. But actually the bigger picture has definitely more items to it. So in the beginning, of course, everybody's only talking aerodynamics. So that's just one sector when you design an aircraft. But besides the aerodynamics, there's something which is really important when we are out there and we are flying a plane. Very often I see people talking about that plane has a lot of performance. They're talking about this. The performance is amazing. And then when I ask them, what do you think? What do you want to describe as performance? They say it's turning nice. They say it's really doing that what I want from the plane. It's not complicated to fly. And actually, in the first degree, that is not bound to the aerodynamics. It's way more bound to a different topic which you could call flight mechanics. And these both things really determine how much performance a plane really has, and how good the handling really is. And a lot of people are really mixing up performance with handling. So this is plainly, oh, it's not blue at all. So maybe, yeah, you want to set it up a little bit different with graphics. Yeah, there we are.
Black is okay.
Black is better, right?
Yeah.
Back to black. And this is what people think about when they set up their planes. It's mainly about the handling. What the distributors and the designers and maybe even the builders of the planes, the companies try to tell you is that the plane has a much better performance now. So I always give this kind of example. Given that you have an aircraft which will grant you 100% performance, will be the best performing aircraft for your class, but you are able to control it that way that you get 90% of the performance out of it. All in all, this sums up, it multiplies so that you have an all-in-all performance of 90%. So what would be if you have an aircraft which has 95% of performance, but you get everything out of it? Then all in all, you might get a better all-in-all performance. So it's not only the aerodynamics. When you tear it down to only the aerodynamics, then it's mainly two parameters which are describing the aerodynamics of an aircraft, where you can measure the quality of performance and the quality of the aerodynamics. And these are items like the L/D, which is known as glide ratio, and the second performance item, which is way more important for F5J than, for example, for an F3V plane, is called endurance parameter, and this is just the L lift to the power of 3/2 divided by the drag. This determines your endurance. So there's a larger number of lift determining your minimum sink. So this is the glide ratio. And this is the minimum sink. Or for a motion plane, the maximum climb. And they are on two different spots on your polar. Maybe, go a little bit into the theory now. You have seen a polar diagram, which is maybe looking like this. I inverted it because we are sinking, we're not climbing here. So on these both axes, we have the velocity over ground and the velocity of our sink. In the coordinated system, it's x and z, but it doesn't matter so much. And right now, for example, a typical polar, sink polar, might look a little bit like this. I'm very happy with what I'm drawing. So, and it's quite easy. In here, on the left end of the polar, we have the stall speed, whatever it might be. Let's call it 5 meters per second. And here we have 10 meters per second. I'll try to be as accurate as I can with this pen. 20. Okay. And in here we do meters per second as well. You can recalculate it in yards if you like. Not so much familiar with the imperial system. So
Times 3.
yeah, let's say this is 0.5 meter, 1 meter, 1.5 meter per second sink. And this is what the plane is doing when it is just flying with no G loads, just 1 G at a static glide. When you do it, when you pull the plane up, so that you get slower. At the point, everybody knows, yeah, you will get a stall. But as soon as you go faster, you will come to one point. It's the first important point on this polar. I'll do it in blue. And this is the point where a parallel of the x-axis, of the v-x-axis, is meeting the polar. That's the point of your minimum sink. When you fly slower, you will sink faster. When you fly faster, you will sink faster as well. So when you want to stay airborne as long as possible, you should fly at that speed all the time. Then we have another point. This one would be the red one now. You take the 0 point of the both axes and put a tension upon the polar. Just to do it like this, bam. And then you have one distinct line which meets the polar here, which actually happens to be at a higher speed and at a higher sink rate. And this is your point of your maximum glide ratio. That means every portion of lift to every portion of drag just calculated to be on that point. That's your maximum glide ratio. And you can't change it as long as you don't change your aircraft. That will be the maximum glide ratio. You can change it when you use flaps, for example. You can change it when you use ballast. The maximum glide ratio is not affected that much, but the speed where the maximum glide ratio occurs definitely is.
Philip, across all the different manufacturers now of F5J models, what's the variation in that glide ratio? Roughly.
Roughly, I can tell you for the Samba planes, because I designed them, between the normal PK and the PK Pro, it was about 1.6%. You can calculate for the same wing loading actually.
Improvement on the Pro as opposed to.
Yeah. And the improvement on the Pro is really like that you have the polar always on top of the other. So there's no cross point.
If you were to guess across all the other different modern, the latest, the top 2 or 3,
I would say yes. I would say you're in a range between 1 and 2% maximum. And we're talking the latest and greatest gliders, of course. And there you see how important the performance really is. It's not that much. Because this is a totally different topic where you can tweak on. This is very important to know how it works. For example, Mehmet was coming along and he was asking, how do you know when to fly which flap setting? And I have a big advantage because I can calculate it, and afterwards I can go out and try if it's really calculated the right way. That's much more difficult if you have no idea about how the glider was designed. What I try to give with all the GPS gliders is exactly a polar diagram right now, so that people can understand when to switch their flight phases at which ballast situation. Because there are 2 main topics where you can change this polar. Nice. She has a very bad glide ratio. She tried to figure out what flap settings to use. Nevertheless, you have 2 possibilities to change that, this polar diagram. The first is using flaps, the second is using ballast. I try to be a little more accurate. For example, this would be flap in 0 position. Now what would happen if I would put the flap in thermal position, like 3 degrees for example? The polar will look somewhat like this. So you see the glide ratio actually got worse. But the minimum sink got there. This is why we are using thermal flap when we want to go up, because you have less sink rate. The same thing is when you just want to float and there's not that much headwind like today. You really want to put your glider in the right position. And this is very crucial to understand. And what's quite good with the GPS right now, you can understand immediately, because you have it on your tablet on the ground, what kind of flight speed you're having. And then you can shift your switches to the according flight speed. In F5J, there's a little bit more connection between knowledge and feeling. That's for sure. But what's for sure as well, if you want to fly home and reach your spot in the wrong setup, you will never make it. Because the next thing is you can as well, when you have a headwind, for example, let's do this now for negative flap. It might look like that. The maximum glide ratio might not change, but if you want to get home with a headwind and you need to be faster than 20 meters a second, it means you have 10 meters a second airspeed, 10 meters a second wind speed, which sum up to 20 meters, then you are better if you put your glider in reflex. You can read all this very well written in a book from Helmut Reichmann, which is called Cross Country Soaring. It's for full-size gliders, but it explains everything in here. If you want to, I can write down the name of the book. You will find it on Google, still available. He was a 3 times world champion in full-size soaring, and he was a teacher as well on the university in I think it was Saarbrücken. So he got it quite right to really write it in a way that you can understand it easily.
Philip, another question then on that. Given the work and the data that you've collected with GPS lights or our type of models, would you say most F5J pilots fly too slow when coming back and not hitting the speeds that give you the best polar?
Most probably yes.
Yeah.
Even a lot of GPS triangle pilots fly too slow.
Yeah.
It's just because it's our natural, I would say, behavior is especially duration glider pilots. We want to stay airborne, and the first movement we learn to stay airborne is pulling up.
Which goes down.
Which is true in a way. You can stay airborne, but you won't make it home, because it's two different things. Staying airborne with a lot of wind, like imagine a free flight glider. It doesn't care, it doesn't need to go home, it just goes. It's in a it needs to fly on that polar always in the minimum sync configuration. But then you need to walk to bring it back. Yeah.
Greg Lewis tends to fly sport class forward ballast.
Yeah.
He likes it like that because he hit the air at the go. Nick Wright used to fly distance heavier than speed very often, and his theory was if you didn't hit air, it will work.
Absolutely.
If you don't hit air, you'll only get the same distance if you put a otherwise you just finish in a shorter time.
Absolutely true. You need to understand what's happening when you add ballast, for example. I don't have a green pen, as I figured out. Green is not working that good. But for example, if this would be our glider at 1.5 kilos, for example, which is a standard weight, what would happen to this polar? You know, I have the polar for flap up, flap down. What would happen to this polar when I fly it at 2.5 kilos, for example? How would it look? Pay attention, it would pretty much look like this. In zero flap configuration. So even if you fly a light aircraft and you reflex it, you will not reach the performance of the heavy aircraft when you need to fly, let's say, faster than 10 meters per second. And this is what you need to understand and what you really can practice to fly with ballast whenever the weather is windy. You might need to take a little bit higher start because your sink rate is worse, but you can penetrate much better. As soon as you need to fly faster than a certain ground or flight speed in that case, then it's mainly always better to change your wing loading to a higher wing loading by using ballast. And that's true for F3B as well. It's just in F3B you have one big problem. You need to get the ballast up by a winch launch.
Yeah.
And that's another optimization point, because the lighter aircraft will launch higher than the heavier aircraft. So, but yeah, there we go from one end to the other. What's maybe more interesting is this area with the flight mechanics. And to flight mechanics, you can definitely put something like the plane design, and you can put something like the plane setup. With the design, not everybody is able to build their own planes, so they need to take something which was developed by maybe somebody else. But with the setup, you definitely can follow some rules which are physically, aerodynamically based. And then there are some topics which are totally up to taste. I'm sure a lot of you will go home a little bit disappointed when I will tell you that, for example, the CG of our aircraft mainly has no effect on the plane's performance. It's really like that. It has a lot of effect on the plane's handling. So when you like to fly an aft CG because your plane is feeling more neutral, more agile, you can turn it quicker, you can get the thermal better, then you can get more performance out of that aircraft because you're used to fly a handling characteristic like that. Steve.
So just before you move on to flight dynamics, just going back to ballast, I'm asking dumb questions here so it sparks more discussion. So we understand the right ballast, the right flap setting for your best glide angle. If you're over ballasted, let's say by 200 grams,
Yeah.
what's the disadvantage in medium thermals?
The disadvantage will be that you don't climb that fast. And a real disadvantage will be when the thermals are narrow. Because these polars which you see here, they reflect a plane in steady flight, wings level. As soon as you bank it, what you definitely do when you thermal, you will have the problem that with the bank angle, your polar will get worse a lot. And this depends on the gravity of the Earth. So in here you're just facing the whole wing area, so you have the whole lift which needs to counter the gravity of the Earth. When it's 45 degrees, it's pretty easy to calculate. It's 1.41 times the amount of lift you need to fly at the same speed. It's the square root of 2 actually. When you do a bank angle of 60 degrees, you need 2 times the amount of lift to stay airborne, or just to fly at the same speed like when you fly level. That's the thing.
I guess what I'm trying to get to is that if you're over ballasted, you'll naturally get to the air quicker. Possibly.
Definitely.
And then, but once you're in the air, after 2 minutes circling in medium air, are you 50 meters lower, 100 meters lower than a model that's 200 grams lighter?
It pretty much depends on the thermal.
I guess I know it. I'm trying to give people a concept of is it really worth worrying about.
A third topic, which is definitely influencing this. This is the, how would you call it, the surroundings, the weather, the conditions. So I call it conditions. And this is something which you really need to practice, which you need to understand, but you can help yourself if you put this into a diagram. The full-size gliders, they're doing this. There's one diagram from Horstmann which is categorizing thermals. Of course, thermals are never the same, but you can tell, are the thermals big, are the thermals narrow, are they strong or are they soft? This is something which we always can do. It's easier for GPS triangle because we have a variometer and we understand, the whole day I had intermediate thermals within 1 and 1.5 meters per second climb. That was my Interglide. And then you hit a thermal with 2.5 meter per second. You can understand that's an extraordinary thermal today. This is a big advantage when you fly GPS. But in here, yeah, it's about the feeling as well. Today I would say we had 2 or 3 boomer thermals. We were up at outspec in 3 minutes. But mainly we had thermals which were not super narrow, not super wide, but manageable. And when you know that as soon as you bank your plane 30 degrees, you need to have about 30% more lift. When you bank your plane 45 degrees, you need to have 41% more lift. And some thermals, and now we're coming back to that, when they are generous enough, maybe not strong, but generous enough to allow you to not bank and yank, then you can take 200 grams more ballast. Because you don't need to generate that lift. If you have a very light aircraft in very light conditions where the thermals are narrow, then you should not use too much ballast, because otherwise you can't do that bank and yank tactics, and you just hit the thermal half of the turn, the other half you're out, or you're much too fast to really climb. That's the thing. And this thermal model is divided into A1, A2, B1, B2. Maybe you can read it up. It's out of the 70s or 80s where they calculated full-size glider performance with that. And you have strong thermals and weak thermals. And you have narrow thermals and you have wide thermals. I would say today we were more on the wide side than on the narrow side, if you would agree.
Yeah.
Sometimes you even could stand there and hop from one thermal to the other with not doing a circle. It worked for I think 2 or 3 groups. That means there were maybe not super strong, but wide thermals coming through, large cycles. And for, let's say, weak and wide, you can't. It's possible to fly too heavy without a lot of panels.
What weight were you flying at today, Philip?
At 2.2 kilograms.
2.2.
Yeah.
All day.
Yeah, all day. I felt pretty
Which
comfortable
I guess
with
would
it.
be heavier than most flying.
If the thermals are narrow and strong, then you really need to chug. Because narrow and strong means mainly when that there is wind. When it's just a narrow thermal and it's strong, then I would say it doesn't matter that much it's strong. I would rather fly a little bit too light to stay in the thermal. But whenever thermals, that's what I think. Whenever thermals are narrow and strong, it's bound to turbulence on the ground, it's windy, and they just build up. And then, that for me is the most decisive point. And then I decide how to cope it with the polar. When I think they are so strong that I can get the light plane up and come easily home, then I rather would fly a little bit too light. When they are intermediate strong, and going downwind very, very far, then I try to place my plane as best as possible, not banking it too much because I know this will harm my performance, but I still can use the better glide ratio to come home. So this is where we always need to figure out what is the wind speed. So when it's weak and narrow, now you can answer this very easily. What would you like to do? Weak and narrow, very light. Despite when you have a lot of wind and you even can't decide is there thermal anymore or not. It's just like where you stand in the air. If you need to push your plane to make a lot of ground because it's too light, then it's not good. But given that weak and narrow thermals maybe mostly occur with very light winds, this is what you do. And then wide and strong, of course, yeah, everything will go up. But if you need to come home, you should definitely choose to fly a little bit more heavy. Or really heavy. Yeah. And this is something which might help you when you go out there and you practice. And after your practice day, you can try and figure out how was this day developing. What did I do? Did I ballast it right? What happened after I ballasted? Did I feel more comfortable? I think it's definitely a big aid to ballast the plane for practice, to figure out the handling of the plane, because it gets more prone to tip stalls, it gets more prone to stalling the plane, especially when you think you're in a nice thermal and you pull it the way you're used to it and suddenly it's stalling. So therefore I really recommend to go out and categorize the conditions you have today. I would say today we were about here. Wide and intermediate strong. So that tells me I'm possibly better off when I'm a little bit too heavy. Yeah. So that's what I choose today. I got smashed down one time where I chose to do a relatively low launch and I got punched. But the other flights were, I was quite happy. Okay, so back to handling. What is happening when a designer is designing an aircraft? He is thinking about the control and the control balances and the behavior of the plane. So how quick can I turn the plane? And how good is the plane when it's flying on itself? How stable is the plane? How forgiving is the plane when you just put an input into it or a gust is coming? How easily will it just dampen out these kind of inputs? Might it be from the pilot or from the weather, from turbulence, to fly, how to say, a little bit more stable on itself? The first thing to know is the further aft you have your CG, the more neutral your plane flies. It's just a little bit like, maybe you have seen these wind, I don't know how it's called in English, wind pointers. They look a little bit like this, like a small thing which is turning on a pivot point. Weather vane. So, and this is pretty much explaining the how the CG on our aircrafts work as well. When you take a weather vane and you put a heavy lead part on the front part. So when a gust is coming and you've moved the pivot point to here, let's say, then it would do nothing. But when the wind is changing direction, let's say over a minute, then it would definitely follow to this direction. But it's not doing any crazy movements out of gusts or so. If you move the pivot point back, then it's looking totally different. It will really go like, okay, it shows you every movement, and at a certain point of pivot point movement, it will just spin. It's unstable. So it will not show you anything anymore. And it's very much the same with our aircraft. In F5J, I understand that we want to use the plane as a device where we can judge just visually what the air around it does. So if it does like that, or if it just slows down, or if it just speeds up very quickly, and so if it's changing its attitude very quickly, you can understand what the air around it is doing. So you can adjust, like, okay, I need to circle there. Oh, I got swamped to the left, so I need to go to the right. Maybe there I can enter the thermal. These kind of things. The second thing is, if you just stand somewhere and it's turbulent, and if you want to relax, and if you want to understand what the air is doing mainly, and not what only the gusts are doing, then you might be better off moving the CG a little bit more to the front. Of course, the plane will not show you everything anymore. So this is where you really need to take care about what type of flying fits your style the most. I can tell you, if you're flying in conditions where you should avoid as many inputs as possible to your aircraft, because you have almost no lift, you're floating around, then when you're sure that there are no real thermals really visible where you need to bank and yank, then you're way better when you put your CG to the front. The plane will fly maybe a little bit faster, but it will not sink faster. That's for sure. You will cover a little bit more ground. But you can understand that you can fly much more relaxed. And over a time of, let's say, 10 minutes, if you put in, let's say, 20 or 30% less of the inputs to your plane, it keeps more energy, it keeps more altitude, it's not sinking that fast. So this will also help. Next question.
In changing the COG on typical geometry of F5J, roughly how many millimeters are you talking of to make that sort of difference that you're talking about?
I would say on that aircraft it could be about 10 millimeters. So it's really something. I'm astonished what some people fly, and they're really successful with it. So I've heard from some Czech pilots they're flying this aircraft at a CG of 118, and I'm flying at 108.
They've got bigger balls.
So, but the case will be, it doesn't come home against the wind better than that aircraft. It doesn't have one digit of glide ratio more at the same wing loading.
So Philip, would you change or adjust the CG depending on the conditions?
I actually, on this aircraft, I do it a little.
Yeah, with the battery.
With the battery,
Yeah, we all.
but I switch it between 108 and 112.
Yeah.
And I've flown it not a lot before I came here, but I was flying it one evening where we had really calm air. I was pushing the battery as far back as possible, and I could really understand, okay, it signals the air better. Not only the lift, everything, of course, but in GPS, to be honest, I'm not changing the center of gravity. Yeah,
Because you're flying much heavier.
no, that's one case, but the other case is you always hear
Yeah.
what the air is doing. We have a variometer,
Yeah, yeah.
and then I can understand, okay, I was flying a lift or I'm not flying a lift, and thereby I choose a more stable aircraft, because very often you want to take a look upon another aircraft, maybe you want to take a look upon your tablet, and you want to have the aircraft flying straight, and the trimming of the aircraft. Again, like that, if you now put an input in, and you have the pivot point very much to the front, you can clearly see, okay, it's veering off by 2 degrees. And by adjusting the speed on the triangle, it's very good if you just have 2 digits and it's really adjusting the speed. If the CG is very far back, it could adjust the speed immediately, and you re-pull a little and it's way too neutral, and thereby I like the CG way more to the front on a GPS aircraft. I understand there are some really skilled pilots out there flying F5J from very low altitudes, and they use a very aft CG just to be able to maneuver this aircraft, which probably I could never do, but they are successful with this. But it doesn't matter that it fits every pilot's skills and style. So what can we do to get a better handling of our aircraft? Of course, if you take a look back, I would say the last 15 years, and you take a look upon the aircraft which were built 15 years ago, let's say a Pike Perfect, and now the Prestige 2. How did they change? If I even go further with old F3B aircraft where we had V-tails which were even looking very small, you can understand, all in all, you would definitely understand that the tail sizes were increasing, the lever arms were increasing, the dihedral was increasing as well. And this is something which definitely has a huge effect on flight mechanics. So if you have an aircraft which is rather old and having a small tail, so it's understepped or underfinned if you want to, you might need to fudge it with a little different setup on your plane. But if you have a plane which is definitely designed to have a large fin volume, a large vertical tail volume, and a large horizontal, a fitting horizontal tail volume, then you might not need to do any kind of strange mixes on your plane. So there are some mixers. So you definitely have some setups, some phases, some flight phases where you have the camber flap set. But then there are some mixers. We can do this with our modern transmitters, which are helpful in increasing the performance through to better flight mechanics. And one of this, for example, is a mix which is called, I start with that one, aileron to flap mix. When I do an aileron input, my flaps are moving with the ailerons. In former days, people were always thinking, oh, I want to do as less input as possible because it induces less drag whilst I'm putting this input in. And that's not mainly true, because on a wing like this, when we are flying, we mainly always are flying with creating lift. We're not flying like a bullet down. Or when we are flying very fast, we're creating very little lift, but the slower you fly, the more lift you create. And thereby, I'll take this plane just to explain it a little better. We need to roll the aircraft. And by rolling the aircraft, we put some aileron up on this side. Imagine we put the aileron down on the other side. What will happen is that the lift distribution over the wing will change at the moment where you induce the rolling motion. As soon as the plane is rolling without any force anymore, the lift distribution will be perfectly elliptical again. So you have this inertia point where the rolling starts, and as soon as it rolls, then you don't feel any lift imbalance anymore. A lot of people get this wrong when they start driving their car and they're putting their hand out of the car. And then they create lift by changing the angle of attack, and you can really feel it. But they don't do the resulting force. They keep their hand out and they feel the lift force. But what's happening to the plane is it has a resulting force which results in a rolling motion. So actually, if you do this, your hand should roll around the car, which it doesn't. But this is what happens on the aircraft. And in the beginning of flying, the Wright brothers figured out the minimal induced drag while inducing the rolling will occur when you twist your wing linear. They had no ailerons, they were just twisting the whole wing. And this creates the less induced drag possible while inducing a rolling motion. So thereby, now we understand, if I move this aileron up, I will have a gap in here, which definitely shows a gap in the lift distribution as well. When I just twist the wing, there's no gap. So the lift distribution is just bent in the best possible way so that it induces as less drag as possible whilst rolling. But we have more surfaces, so we just can try to get as close as possible to this equally twisted wing, linearly twisted wing. And it's very easy actually to calculate for every aircraft what is the best mixing ratio of aileron to flaps, and it even doesn't matter how many surfaces you have, even for 6 or 8 surfaces, you can calculate this. And it's just a little geometric task that I can show you on the board. example, take the wing. We have the fuselage in the center. In this one, it's just one point, okay? And then we have ailerons all out to the tip. And just in this case, we do it like the flaps are as long as the ailerons, okay? So, no dihedral in this, just for explanation. This is the fuselage. So, the length in here is always the same. Let's say X. For example, on a 2-meter aircraft, every flap would be 50 centimeters. And it's okay. So, now if we twist this linear, it would look a little bit down here. Like that. I would be better off with a ruler, but you can understand. So in here we have 4 individual flaps. And what we see right now, it's very important to measure the center points of each surface to assimilate this linear twist as good as possible. For example, now you really need to pay attention. We are moving the ailerons by 10 degrees, okay? 10 degrees up, 10 degrees down, no differential. And they're all equally long. So we go back to this 2-meter wing. Where is the center point of this aileron? At which distance?
75 centimeters out.
75 centimeters. Where's the center point of this flap? 25 centimeters. And now, give me a ratio. This is 100%. So how much is 25 from 75%? It's 33.2.
Which is why so many manufacturers say about a third of mixing.
You're right, absolutely. Now what would happen if your flap is less long or less span than your aileron? You can see that proportion gets smaller. Let's say 75 by 20. Maybe you need to pick out your handy dandy calculator, and then you figure out, okay, it's 100 to 29. Or one, yeah.
And that ratio never changes regardless of the conditions.
It never changes regardless to the minimal induced drag. We will come to that a little later. You're super smart. Super smart. But this, even if you have 3 or 4 surfaces, you can always measure from the center of your fuselage to the center of the first surface, to the center of the second surface, to the center of the third surface. Then you take 100% of your throw from the outboard surface and recalculate the absolute perfect ratio by these points. So that's all about it. Yeah.
What effect does the wing chord have?
Pardon?
The wing chord, which is, say, elliptical flank.
That's a different topic. It doesn't have actually an effect on the aileron input. At most of the cases, as long as you're flying fast enough. The wing chord distribution is more like when it's super elliptical, that means you will have local lift identical in the center as on the tip. But due to Reynolds numbers effect, the tip is much more prone to tip stall because you have a larger boundary layer upon it. And this, can can stall earlier because it's not as stable as a thinner boundary layer. So now the loop closes. Attention, Mr. Haley. When you fly your plane very slow and you have a intermediate to aggressive taper ratio, that means the taper ratio is if you have a high taper ratio, then your tip is very narrow and your root is very wide. If it's the opposite way, then you can say this plane is more prone to tip stall when it's very narrow on the tip, and when it's not very narrow on the tip, it's a little bit more stable tip stall. Why do we want to have the tips very narrow? Because we want to save induced drag. We want to be as elliptical as possible, but the next part would be practical reasons. It's lighter, it has less volume, so the inertia is playing a role as well, which is definitely a fourth topic, which is affecting the flight mechanics as well. It's not only about flight mechanical calculations. When you put the inertia in, then it's another topic. Nevertheless, to go back here, right now, this I'm using mainly for all my flight phases despite thermal. The slower I fly, the more I fudge this ratio. Because what will happen when I'm flying very slow and I need to deflect my aileron a lot, which I need to do because the slower I am, the less effective is my aileron. But the slower I am, the more I want to have this tiny little thermal and I want to go in there. But I don't want to risk a tip stall. So then, and only then, I do it like this to have the same roll rate. I reduce my aileron throw because I don't want to have a tip stall. It's the least I want to have. But to regain this roll ratio, I increase this ratio, so I put more aileron to flap mix the slower I fly. On this plane, it's actually 100 to 75. Yeah, because I can reduce my aileron throw by about 20% to 80% of the original aileron.
I'm going to ask a question that you're not going to be able to answer. So why does a very well-known pilot, Ariane, fly no flap aileron at low level? He's got ailerons doing that almost air brake to spin it on an axis.
I don't know.
I don't get the theory behind that.
He induced the tip stall.
Well, he almost is stalling it when he's
Maybe
doing his
he
10 meter
exactly
launches.
knows when the tip stall goes.
Yeah.
But
Completely
to me, it
different
doesn't make
setup
sense
to
as well.
how we
Yeah.
would normally set a model up.
Yeah.
How much differential would you use?
Next point. How much differential would I use? Yeah, because in here I think we're pretty much done with this first thing, which I call ail to flap mix. And now the next mixing is coming. And yeah, you can put your stones out and throw them upon me. It's called aileron to rudder mix.
That's a controversial one.
That's a touchy subject.
We don't have this in full size, so we don't use it in box as well. Yeah, and it's mainly very largely connected to differential. Why are we using differential? Because we don't want to have an adverse yaw motion. What is adverse yaw? Everybody knows when your plane is rolling and it's rolling exactly along the fuselage axis, then there's no adverse yaw visible. Adverse yaw would be when it's looking like this. Pretty much like that.
I was going to say in full size, you are taught to do that mixing automatically because I remember at the age of 15 being clipped on the ear hole by the instructors behind me. So I think it's still there.
He's super right. You know, when you sit in the aircraft,
It's just in your brain.
it's a different thing. You don't have servos. You have no possibility to mix, which definitely has an effect, and you could lose your life. It's hard, but with these planes, it's really difficult to lose your life. I know it might be possible, but not in the case like when you're sitting in a full size. So what would happen if you fly a K-21, for example, and the rudder cable breaks. You have no rudder anymore. Then you just can counteract this adverse yaw with differential. So this is one main reason why the full-size gliders are putting a differential in. And differential, or adverse yaw better to say, adverse yaw is highly depending on the flying speed. Actually, because of it's highly depending on the lift you are producing with your wing. And now, attention. I twist this wing now. This is the aileron motion. Okay? So from the side it would look like this. And the result would be this. What is happening there? We have a lift distribution which mainly looks like this. It's a little less lift to absolutely no lift on the very tip, to the highest lift proportion in the center of the wing, and then it's going to low lift distribution here as well. Low lift coefficients. And what people get wrong is, when you start a rolling motion, they think in this moment on that wing, which is going down, I need to produce negative lift, which is not true. You just balance the lift. There's still an upward lift component, but the lift component here is higher. So the distribution might look like this, or vice versa. If you fly straight down and then you put an aileron motion in it, so you fly at no lift coefficient, then you're right. Then you just can turn along the axis of your fuselage by inducing negative and positive lift. That's true. So we're flying at a decent airspeed, let's say. So not too fast, not absolutely slow. Right now we are having lift. Thumbs are showing the lift. Okay, this is the lift component which is counteracting the gravity. So thereby I can fly. And now I induce an aileron motion. Take a look. What happens to my thumbs? And that's all where the adverse yaw is coming from. It's an imbalance of lift vectors. So the lift vector of the wing, which is putting the aileron up, is actually pointing forward. The lift vector of the aileron you put down is actually pointing backward. And now, by just taking a look upon where I point with my thumbs, I can see what's happening to this adverse yaw. Take a look. Looks familiar, doesn't it? So how can I counteract this adverse yaw? You need a little more time, but the circle will close. I can either put a certain amount of rudder in and counteract it by a lifting force on the rudder. It's a lifting force in the right direction, which is counteracting this imbalance of lift. I can also do it by just putting an aileron up. This means this wing is creating lift and drag at the same time. This is lift and drag at the same time as well, but the proportion of drag and lift in here is increasing more than on that side. But you still have the lift imbalance. So you can see that if I put a certain amount of more drag due to the configuration of the wing in here, it can counteract this lift imbalance, but by inducing more drag. If you do it with a rudder, first of all, you're inducing only more lift. And there you see, every proportion of lift divided by every proportion of drag is my performance parameter. If I produce less lift but more drag, my performance is going down. So with every differential which I need to use, it's actually less performant than when I put a little bit more lift on the rudder. Therefore, I'm strongly recommending to install your glider with aileron to rudder mix rather than using differential. there are limits to that. I would talk about this as well. This, as we've seen, is mainly depending on the lift. The more lift I have, if I do it with a little lift only, I'm flying very fast, then this imbalance is almost not occurring anymore. And therefore you can understand when I'm flying speed task, I don't need any differential and any rudder input. It's rolling. The slower I fly, the more lift imbalance I have because my thumbs are growing and I have this motion and I need to counteract it. So what I do, I go out on the flying field at not conditions like today. I would do it in really calm air, and I would definitely watch the axis of my fuselage, and I'm installing my plane with 0 differential at the beginning. So every motion up equals every motion down, because there I can get the most roll rate. When I reduce the motion down, I have less effective aileron throw, less effective roll rate, less roll rate in the end. So that's the first thing I do. And then I install the speed which I want to have the plane fly. So that means no camber at all, camber flap in 0 position, it flies with this speed. That's what it's used to. And then I give full aileron left and right. Not too fast, not too slow. And when you have the full aileron, you instantly go to the other side. You don't stay there. And then the plane should do exactly this. And it's very easy to judge if it is yawing or not, or if it is skidding as well. And when I see it's yawing, I put more rudder mix, until I have the perfect axial roll for that speed. Then I do it again for the next flap set, because there is no perfect aileron to rudder mix for the whole flight envelope, because it is depending on the amount of lift. So you go slower, the more amount of lift. So then I go up to 100% aileron to rudder mix. If this is not possible to still counteract the adverse yaw, then I start putting in differential. On a plane like that, it might be very soon that I need to put in differential because it has a very low rudder volume. On a plane like, for example, a Nimbus 4 full scale, whatever, or scale glider, which has a huge aspect ratio but a relative small rudder, same thing. When I'm slow, sometimes I need to put in the differential, but just after I've reached this maximum rudder throw coupled to the ailerons. So does that answer your question?
In a way.
Yeah. I know that there are people flying on the slope and they like to put in differential rather than putting in rudder mix, but this has different reasons, especially on the torsion force of the tail boom, which you don't want to just be sluggish. No, it creates drag but lift at the same time. And whenever you create, to every drag you create at the same time a little bit of lift, you raise the L over D. It's just mathematically true. If you only add drag, you're lowering it. If you add a little bit of lift but a large number of drag, of course the L over D gets down, but it gets less down than if you would have no lift component at all.
If you are actually circling,
Yeah.
because the rudder becomes down elevated,
Yeah.
would you start filling off again?
No, the plane actually doesn't see this coordinate system you are seeing. The plane, for the plane, it doesn't really matter if it's flying like that or that. It just sees, so to say, a higher lift component which it needs to create to be on this radius of circle radius. But it's not like elevator or rudder is different in that kind of way. It's more depending on what kind of what proportion of lift you really need to sustain the flight speed you're at right now. One more question.
I have a question. There's lots of people who talk about flat turns using lots of rudder, and I hate that, so I wanted to...
It's possible when you have a motor, when you have a power plant. Maybe you have seen these 3D aircraft.
I mean more in the glider sense,
Yeah,
to
exactly.
thermal efficiency.
There, it is not possible.
You're saying basically balanced turns.
So if you want to have a certain turn radius, this is a large turn radius, this is a narrow turn radius, and we of course want to have, when the thermal is strong and when the thermal is light and narrow, we want to keep in this core because there it's the strongest, and we of course as well we want to have as less bank angle as possible, and it's not possible. It's really just depending on your weight of the aircraft, and the bank angle in the turn is determining the radius, nothing else. Because to stay on this steady turn, it's necessary to create a lift force which is facing into the circle. When the plane is light, you can keep this radius at a lower bank angle. When the plane is heavy, you can't. You just need to bank more and be faster and come down faster. So therefore, again, there is no flat turn which you can do with the rudder. It's just a coordinated turn that when you are turning your plane, even there you still want to have it rolling axial, and this axial rolling is contributed with the rudder, but on the other thumb, whatever mode you're flying, you're pointing the rudder into the turn, of course, not to have a yawing motion there or a skidding motion there. You want to have mainly your fuselage axis always perpendicular to the turn radius. It's okay? Good. So, what we can do before dinner is, we can make a little space here, and I can show you how I'm installing my setup to my plane. Because what I really figured out, it's really nice when you have designers as well as producers giving you a sheet which is mainly good for a good start. And it's plainly not possible to do that when you measure millimeters and so on. So I do a different technique right now. A lot of people overtook it as well with inclinometers, where you can see all the degrees. So that's mainly the same for all aircraft. And with this background here, I'm sure you can install a nice setup on your planes as well. So what we can do is we can put the table a little bit closer to here,